for the do now, I put 4 multiple choice questions. So these are 4 practice multiple choice questions that refer back to units 1, 2, and 3. So the first question, this says based on Coulomb's law. So before I even read further, I'm going to underline Coulomb's law. And I'm just going to remind myself that Coulomb's law refers to charge and distance when we think about strength of attraction. So based on Coulomb's law and the information in the table above, which of the following cations is most likely to have the weakest interaction with an adjacent water molecule in an aqueous solution? So weakest interaction. Think about Coulomb's law, what that would mean about charge and about distance. So if we want the weakest interaction, that means that we want the lowest charge. So we would want the lowest charge. And then in terms of distance, if you want a weak attraction, they're going to be far apart. So we're looking at the lowest charge and farthest apart. In terms of farthest apart, that would be the largest ion. And so if we look at our answer choices here, again, Coulomb's law is charge and distance. So if we know we want the lowest charge, eliminate your higher charges. They give us the charges here. I'm going to eliminate C and D. Those are higher charges. Higher charges result in a stronger attraction. So now we're between Li plus and Na plus. So now those have the same charge. So now what we look at next is the size. The larger the ion, the farther apart the ion's nucleus is from the water molecule. And so the weaker the attraction. So if you look at your periodic table, Li plus and Na plus. Well, Li plus, its valence electron is like helium's valence electron. So that would be in the 1s. Na plus, its valence electron is like neon, so it's in the 2p. So Li plus has a valence electron in the n equals 1. Na plus has a valence electron in n equals 2. Which valence electron is farther away from the nucleus? Na plus. That's going to be our answer. The reason that it's Na plus instead of Li plus is because Na plus is a larger ion. The larger the ion, the weaker the attraction. We're looking for the weakest attraction here. Number 2, at room temperature, I2 is a molecular solid. I2 is a molecular solid. Based on what we talked about yesterday, molecular solids are held together with intermolecular forces. A molecular solid is made of nonmetals. Which of the following provides a characteristic of I2 solid with a correct explanation? So A, it has a high melting point because it has weak intermolecular forces. Well, the weak intermolecular forces part is true. But if it's weak IMFs, that means it's easy to overcome the IMFs. That would result in a low melting point. So A is not true. The high melting point part is not true. Weak IMFs means it's easy to overcome, so it's a low melting point. B, it is hard because it forms a 3-dimensional covalent network. Well, we know that that's not true of I2 because 3-dimensional covalent network, that's diamond. That's a covalent network solid. I2 is a molecular solid. C, it is not a good conductor of electricity because its valence electrons are localized in bonding and non-bonding pairs. So what that means is that you have a structure that is not resonance, or it's not metallic. Now, if you read that and you're like, yeah, I'm not sure, move down to D and read D. D says it is very soluble in water because its molecules are polar. I2 is 2 of the same atoms bonded together. That would have an electronegativity difference of 0. Phi2 has an electronegativity difference of 0. What does that mean about the molecule? It's nonpolar. So D is not true. So our answer is C. Molecular solids are not good conductors of electricity because the electrons are not able to move. They're stuck in the bonds. They're stuck in that single bond between both of the iodine atoms. Number 3, which of the following molecules is least soluble in water? Least soluble means that it is most different in terms of IMFs. So the least soluble means it's going to have the largest difference between intermolecular forces. Remember, water, we draw the Lewis structure of water, H2O. Water can hydrogen bond. So water contains dispersion forces, dipole-dipole forces, and hydrogen bonding. The more similar the molecule is to water, the more likely it is to be soluble. We look at A. Notice we have this double bond with lone pairs on the oxygen. The lone pairs on the oxygen, that's pulling the electrons up toward the O. That's a polar molecule, so this has dipole-dipole forces. We're just going to go through and label all of the molecules first. Here we have CCl4. Well, notice here, chlorine is more electronegative than carbon. So each of the chlorines are going to pull the electrons toward it. This is a tetrahedral molecule. You have one carbon pulling up, one carbon pulling down, one carbon pulling to the left, one carbon pulling to the right. All of these dipoles cancel out. This is a nonpolar molecule, which means CCl4 will only contain London dispersion forces. In C, notice this OH covalent bond. If I bring another one of these molecules, or if I bring a water molecule near this, what's going to be the strongest IMF? Hydrogen bonding. Because you have H covalently bonded to NO or F. So if I bring a water molecule near this, this H is going to attract to the O in the water. And then finally in D, this is going to be similar to A. You have this oxygen with lone pairs on it. Well, oxygen is going to pull all of the electron density toward it, making that side partially negative. This is a polar molecule, so this will have dipole-dipole forces. So you're looking at which one is the most different. Well, A and D are both polar. Remember, we can use like dissolves like. That's not our explanation, but that's an easy way for us to remember. Well, if water is polar, these polar substances will dissolve in water. Hydrogen bonding is even more like water. C is going to actually have the strongest interactions with water because they both hydrogen bond. B is the one that will be the least soluble because its strongest intermolecular forces are dispersion forces. So the more alike they are, the more likely they are to mix. The more different they are, the less likely they're going to mix. And then number 4, for element X, represented above, which of the following is the most likely explanation for the large difference between the second and the third ionization energy? So this is going back to Unit 1 of the AP curriculum with ionization energy and periodic trends. So here we have the largest jump between the second and the third ionization energy. Well, when we noticed the big jump, we said, well, that tells us how many valence electrons we have. So this element X, this unknown element, if the biggest jump is between 2 and 3, that tells us that it has 2 valence electrons. And the reason that we have the jump between the second and the third, I'm just going to use 3 energy levels as an example. The first 2 valence electrons are being pulled out of, we're going to say n equals 3. So here's the first ionization energy. We're moving the second valence electrons. Second valence electron is the second ionization energy. Now we try to remove a third valence electron, but it gets a lot more difficult. The reason that it gets a lot more difficult is because now we're removing it from an energy level closer to the nucleus. So if we're removing it from an energy level closer to the nucleus, it's going to take a lot more energy in order for us to pull that third electron away. So based on that, if we read through each of these, A says the effective nuclear charge decreases with successive ionizations. As long as you're dealing with the same atom, same element, your effective nuclear charge shouldn't change. That's based on the number of protons in the nucleus. So effective nuclear charge is only going to change if you're changing the element itself. Shielding of outer electrons increases. Well, shielding would increase if we were adding more electrons. The electron removed during the third ionization is, on average, much closer to the nucleus than the first two. That is the correct answer. That is exactly what we had just said when we looked at the energy levels. And then it says, in D, the ionic radius increases. That means it's getting larger. That's actually not true. Remember, the more positive the cation, the smaller the radius gets. So we have B, C, B, C for these multiple choice questions. This actually is this was pulling topics from both units 1, 2, and 3. Any questions on the do now?
What's shielding again?
So shielding is, imagine if you have a lot of electrons in the first two energy levels. Shielding is when you have those electrons, your core electrons, blocking the positive charge from the nucleus out to the valence electrons. So your valence electrons don't feel the positive charge from the nucleus as much because of the number of core electrons. So we see shielding more when we get into the larger and larger and larger energy levels because there's more core electrons. So if we wanted to explain number 3 in a free response question on why why CCl4 is least soluble, what we would say is that the strongest intermolecular attraction between CCl4 and H2O is London dispersion forces. And so because London dispersion forces are such a weak force, it's not as likely to be soluble in one another compared to the other ones which form stronger dipole-dipole forces or hydrogen bonds. So it's just about the strength of the attraction between the two. General overview. So you can see a lot of this actually came from our summer work. So introduction to reactions, net ionic equations, particle diagrams, stoichiometry, types of reactions. A lot of this was chapters 3 and 4 in our summer work. We're still going to go through and review it, but that's where a lot of this came in. You'll notice it's an intro to titration. Talk about titrations a lot more when we get into acids and bases. Same thing with an intro to acid-base reactions, but we will review redox at the very end. So I kind of combined 4.1 and 4.4 on the same slide. 4.1 and 4.4 say almost the same thing. And it's looking at the difference between physical and chemical changes. And we're actually going to tie this back in to intermolecular forces. So a physical change occurs when a substance undergoes a change in properties, but you are not changing the substance itself. So a phase change is a physical change. In a phase change, we are overcoming the intermolecular forces, but we still have the same substance. Boiling water. It's going from liquid water to gaseous water. It's still water. Forming a mixture is also a physical change. So if we mix sodium chloride and water, that's actually a physical change. Creating a mixture is a physical change. A chemical change is when we produce a completely new substance. And more specifically, this is when intramolecular forces are changed. Bonds are broken. Covalent and ionic bonds are broken in a chemical change. Evidence of a chemical change. We see a production of heat or light. Formation of a gas. So if you're in lab and you see bubbling, that tells us it's a formation of a gas. Formation of a precipitate. So if we see a solid form, that tells us we have evidence of a chemical reaction, or if we see a color change. Now, color change, we have to be careful because, for example, copper 2 sulfate is already a blue crystal. When we put it into water, it creates a blue solution. That would not be considered a color change because the substance itself was already blue. So when we think about a physical change, we're breaking intermolecular attractions. When we have a chemical change, we're breaking intramolecular attractions. We're breaking covalent bonds or ionic bonds during a chemical change. And I have this once again. We talked about it yesterday, but I have it up here once more. Intermolecular forces are what are broken during a phase change. Boiling, melting. Those are intermolecular attractions being overcome. So once again, evidence of a chemical change. I just gave specific examples. Producing a gas. So notice how here we have potassium chlorate. We're producing something new and a gas is being produced. That gives us evidence of a chemical change. Forming a solid, evidence of a chemical change. Here's an example of change in color. We put two white solids together. It produces a yellow and a white solid. There was a change in color, evidence of a chemical reaction, and then production of heat. So combustion produces heat, tells us we have a chemical reaction. Here's something with physical changes again. We might see similar evidence. We might see a bubbling, for example. Boiling water, we see bubbles. But that's because we have liquid water turning into gaseous water. You have to think, are bonds broken or not? If bonds are broken, it's a chemical change. So once again, it's a very common misconception. We see it in multiple choice questions all the time. What happens when water boils? When water boils, we are breaking hydrogen bonds. That's an intermolecular force. We are not breaking covalent bonds. When we boil water, we are not producing hydrogen and oxygen gas. We would have to run electricity through water in order to produce hydrogen and oxygen gas. Topic 2 is net ionic equations. So remember that every chemical process can be represented by a balanced equation. Don't forget about the law of conservation of mass. Make sure your reactions are balanced. Mass is neither created nor destroyed. When we're writing net ionic equations, AP wants net ionic equations. To write the net ionic equation, we can start with the complete molecular equation. Then we can break up our strong electrolytes. And then we can cancel out spectators. And so you can go through each one of the types of equations, but we want to end with net ionic. So spectator ion should not be included. Remember, we just need to know potassium, nitrate, ammonium, and sodium. Those are the solubility rules that we need to know. Potassium, K+, nitrate, NO3-, ammonium, NH4+, and sodium, Na+. Anytime we have a compound with one of those ions, it will be soluble. The point of a net ionic equation is to just show what is happening in a chemical reaction. We leave out anything that remains the same in the container. So with net ionic equations, We have to make sure we know the difference between strong electrolytes and weak electrolytes. Strong electrolytes will get separated into their ions. Remember, in order for a strong electrolyte to even be potentially broken apart, it has to be aqueous. That's the only state of matter that even has the potential to break apart. If it's a solid, a liquid, or a gas, it remains intact. So strong electrolytes, we have soluble ionic substances. So it has potassium, nitrate, ammonium, sodium. Strong acids, strong bases. So make sure you know your 7 strong acids. And then make sure you know your strong bases. So remember your strong acids. You have HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. There's our 7 strong acids. Remember the strong bases make that lowercase b on the periodic table. So your strong bases, we have lithium down its group, and then we have calcium down group 2. So it makes this lowercase b. Any of these with hydroxide. So LiOH, CaOH2, SrOH2, KOH. Those are your strong bases. So you need to know your strong acids and your strong bases, and then your solubility rules. If it's aqueous, but it's a weak acid or a weak base, acetic acid, vinegar is a weak acid, that will not break apart. Even though it's aqueous, it stays intact. Solids, liquids, and gases also will not dissociate into ions because they're not aqueous. So only strong electrolytes will break apart. Weak electrolytes remain intact. And I put a particle diagram to show. Here we have the ions separated. Here we still have the molecules together. So you want to make sure you know the difference between the strong and the weak electrolytes. Topic 4.3 is looking at representations of reactions. So to me, what this is focusing on is particle diagrams. So with particle diagrams, few things to keep in mind. As soon as you are given a particle diagram, count your number of particles. Count them. Because you never know what you're going to have to do with it. We can use balanced equations to help us answer questions about particle diagrams. The law of conservation of mass will always hold true, so pay attention to limiting reactants. If you run out of something first. I put an example over here, practice multiple choice question. Says the picture above represents H2 and O2 in a sealed container. What picture would be the best representation of the products if the reaction were to run to completion? They gave us a balanced equation, so we need to use this balanced equation. Notice we have 2 H2s and 2 O2s. Well, here I see that for every 2 H2s, I need 1 O2. So I like to circle in my particle diagram. For every 2 H2s, I need 1 O2, and that will produce 2 waters. So instead of circling, I used a square. So this, what I just drew, is going to give us 2 waters. However, do I have any more H2s to use? No. Which means I will expect to see 2 waters, and then I'm going to have this O2 left over. So try to draw it yourself and see which matches. So I notice here, C and B are tricks. Because notice that the larger blank circle is oxygen. This shows HO2. This shows HO2, so be careful. So C and B aren't even right because that's not water. A lot of people will choose E, but you have to make sure that you take into account if there's anything left over. So that's what topic 3 looks at in unit 4, is being able to represent reactions using particle diagrams. So you have to make sure you pay attention to your balanced equation. Count your particles. So topic 5, because we looked at topic 4 with physical and chemical changes, topic 5 is stoichiometry. And so with stoich, we have a lot of different types of questions that we could do. So with stoichiometry, the biggest thing is to make sure that we're using mole ratios. So this slide gives an example where you're burning C3H8 and you're trying to calculate carbon dioxide. So remember, if we want to convert from one substance to another, we have to use the mole ratio. You want to go from propane to carbon dioxide, you cannot use grams. You can't use a gram ratio because everything has a different molar mass. You have to use a mole ratio. So that's why I always say, when in doubt, go to moles. And if you're ever not sure and they give you grams, start by going to moles. Once you have moles of one substance and you have a balanced equation, you can go to moles of anything else. Other things you can do with stoichiometry, molar volume. Molar volume is on your equation sheet. Under gases, it says ideal gas at STP, 22.4 liters per mole. So if a gas is at STP, we can use molar volume to convert between moles and liters. If we're dealing with gases, we could also use the ideal gas law. Density. Remember, density can either be grams per liter or grams per milliliter. Density is a way we can go between mass and volume. And molarity, moles per liter, is a way that we can convert between moles and liters. So remember that you have other conversion factors that you could use to go between two substances. Molar mass lets us go from grams to moles. Avogadro's number lets us go between moles and atoms or molecules. To continue on with stoichiometry, there are a couple useful equations that are not on the equation sheet that we have seen questions revolve around in the free response. And those are percent yield and percent error. They are different equations. Percent yield is if you're in the lab and you collect an amount of solid. Percent yield is how much did you collect versus how much were you supposed to collect. So it's actual, that's what you actually got in the lab, divided by theoretical. Theoretical is stoichiometry. So percent yield is actual over theoretical times 100. Percent error is how close or how far away from you were you from what you were supposed to get. So that is accepted minus experimental over accepted. So whatever your number was supposed to be, you see twice. Experimental is what you got in the lab. Notice the absolute value because percent error needs to be positive. In terms of the numbers themselves, percent yield, you want a high percent yield. Your goal is 100% yield. That means that you collected 100% of what you were supposed to. You want a low percent error. So you want to be as close to the accepted value as possible. A 1% error is good. It means you are 1% away from where you were supposed to be. A 1% yield is bad. That means you only collected 1% of what you were supposed to. And so I kept everything down here. This is the exact same thing that was on the other slide. But remember, we use stoichiometry to determine how much of something we're supposed to collect. Now, going along with stoichiometry, this is an example problem, so you don't have to write this entire thing down. just know that this is on the slides. Don't forget about limiting reactants. If you are given 2 or more amounts of reactants, so here it says aluminum sulfide and water react, and it gives us amounts for each. Well, if we're given amounts for each reactant, you have to identify the limiting. So if you are given amounts for each reactant, you have to identify the limiting reactant. Remember, the limiting reactant is the one that runs out first. And so here what I did in this practice problem is I used each reactant and I stoiched to one of the products. Now, I read ahead and I saw that it said what mass of H2S can be formed. So I took Al2S3, I stoiched to H2S. I took 10 grams of H2O and I stoiched to H2S. The one that is limiting, your reactant that is limiting, is the one that makes the least amount of product, because that reactant runs out first. And so then if you figure out your limiting reactant, notice that I already answered question B by determining the limiting reactant. So don't forget, if you're given amounts of more than one reactant, you have to figure out which one is limiting. You can't just pick one. And then whichever one is limiting, so water is a limiting reactant, which means if I needed to solve anything else, I had to use water. I had to use water to figure out anything else.
What if you didn't read ahead? Would you have to just...
So then you could stoic to either of the products.
Can you stoic to both? Like one goes to one? Oh no, you do both.
So you would need,
one.
Right. You would need to pick the same product for both, because then you want to compare those numbers.
Yeah.
Okay. But if you did this and you went to aluminum hydroxide, that's fine. You still would figure out the limiting, but then for part B, you'd have to start with water and stoic to H2S.
Okay.
Yep. Topic 6 is intro to titrations. So we're not going to get into a lot of the math with titrations in Unit 4. We'll get into more of the math of titrations in Unit 8. But for topic 6, this is more, why do we use them? What's some important vocabulary for titrations? So remember, the point of a titration, any kind of titration, is to determine the concentration of an unknown. So when we titrated, we were determining the concentration of acids. We used a known concentration of sodium hydroxide. We performed the titration to figure out the concentration of an unknown. So some important vocabulary before we look at the steps. We have the analyte. That's what we are analyzing. That is what has an unknown concentration. We have the titrant. So the titrant is what is in the burette. That is what we know the concentration of. The burette is this piece of glassware. A burette is the most precise piece of glassware that we have in the lab. It's the most precise glassware. We should actually use burettes to create solutions, because we know how precise a burette is. So burette, we're able to add small volumes from. And then we have the equivalence point. So remember, the equivalence point is when the analyte is totally consumed by the titrant. The equivalence point is when we have a stoichiometric ratio. So the equivalence point is where we can use the mole ratio of a balanced equation and we can just perform stoichiometry. The equivalence point, a lot of times we use the term end point. At the same end point is when we see a color change. So this point, when the color has changed, is actually called the end point. The equivalence point is when we are at a stoichiometric ratio. So the steps in a titration: you rinse the burette with the titrant. So whatever you're going to add into the burette, you rinse a little bit just to make sure that there's no contamination. Then you add your titrant into the burette. You have a certain volume of your analyte in the Erlenmeyer flask underneath. You add an indicator, you can add that. And then we add the titrant little by little from the burette down into the flask. We see the end point when it changes color. So we use phenolphthalein to turn that hot pink. For some people, they hit hot pink really quickly. Other people, they were adding little by little by little, and then took a little bit longer. Based on your amounts, your volume of what's in the flask, and your volume and molarity of what's in the burette, we can determine the concentration because it's nothing more than stoichiometry. We use our mole ratio. So if it's a 1-to-1 mole ratio, our moles are equal at the equivalence point. So topic 7 looks at chemical reactions. This first slide is actually reviewing chemical reactions from honors. So this looks at synthesis. Remember, synthesis is when you add two things together. Decomposition is when you take one substance and you break it apart. Single replacement or single displacement, those are the same terms. It's when you replace one substance with another. Typically, we see two metals being replaced. So one metal will replace another. And then double replacement. That's where we have two solutions and our positive ions will switch. They will replace one another. Now this, again, was just a review of honors. What AP focuses on is what I have on the next slide. So if you actually look at topic 7, it doesn't really say anything about synthesis or decomposition. Instead, it talks about these 4. Combustion, acid-base, redox, and precipitation. So I'm going to actually start with precipitation down here. A precipitation reaction is a double replacement reaction. A precipitation reaction is when a solid is formed. So precipitation reactions involve mixing two solutions to create a solid. If a solid isn't formed, it can't be precipitation. Another type of double replacement reaction that we see is acid-base, which is also called neutralization. So when we have an acid-base reaction, that is when we see protons being transferred. Remember, an acid will donate a proton, which is an H+, and then we see a salt and water being formed. So when we have an acid-base neutralization, we have an acid plus a base. It makes a salt and water. Neutralization, because we're forming water. Then we have redox, oxidation reduction. We just talked about redox in unit 10, our unit 10. Redox reactions involve the transfer of electrons. So we can tell that redox occurs because we assign oxidation numbers and we notice that our oxidation numbers change, which means electrons are being transferred. Combustion reactions are actually a subclass of redox. So in combustion, we have a hydrocarbon, some carbon-hydrogen compound reacting with oxygen to produce carbon dioxide and water. We have a hydrocarbon reacting with oxygen, it forms CO2 and H2O. That is combustion. In combustion, we typically see redox. We see oxidation numbers changing. So these are actually the types of chemical reactions. If you look at topic 7, it talks about these 4 types of chemical reactions within the AP curriculum. And so to take acid-base reactions, just kind of one step further, Unit 4 does talk a little about Bronsted-Lowry acids and bases. And so according to Bronsted-Lowry theory, an acid is a proton donor. A base is a proton acceptor. When we talk about a proton with acids and bases, we are talking about an H+ ion or H3O+. And so if something donates a proton, it's an acid. If it accepts a proton, it's a base. Going along with the Bronsted-Lowry definition, we looked at conjugate acids and bases. So remember, once an acid donates its H+, it turns in to its conjugate base. So when HA donates H plus, it becomes A minus. That's the conjugate base of the acid. When the base accepts the proton, becomes HB plus, that is now the conjugate acid of the base. So a conjugate acid and conjugate base, right, any pair, so an acid and conjugate base, a base and a conjugate acid, differ by 1 H plus. Conjugate acids and bases differ by 1 H plus. Remember, we talked about the strength of conjugate acids or conjugate bases based on the acid that it comes from. So if we have HCl, that's a strong acid, its conjugate base is neutral. Remember, you have one of two pairs, strong neutral or weak weak. So when you're looking at the strength, you're looking at how strong is the acid or base that the conjugate originates from. And this shows some examples of conjugate acid-base pairs. When we talked about conjugate acid-base pairs, we talked about water and how water is unique because it's amphoteric. Amphoteric means that it can act as an acid or as a base. So it has an H plus that it could donate, but it also has lone pairs that can accept an H plus as well. So water plays a really important role because it is amphoteric. It can be an acid or it can be a base. And then topic 9 within unit 4 is all on redox reactions. So redox reactions, remember, we have electrons being transferred. So when electrons are transferred, this is a redox reaction, redox for reduction and oxidation. When something is reduced, it gains electrons. So whether you remember oil rig or Leo Burr, it is about electrons. So if a substance is reduced, that means it has gained electrons. If it is oxidized, it loses electrons. You have to be able to assign oxidation numbers. You assign oxidation numbers to every single atom in a balanced equation. Look at the oxidation numbers from reactants to products. The oxidation number goes down, being reduced. If it goes up, it's being oxidized. You cannot have one without the other. You have to have reduction and oxidation together. You do not need to know the names of the agents. So you'll notice in the topics that it says you do not need to know the definition of an oxidizing agent and reducing agent. You do need to be able to identify if species are oxidized or reduced. In terms of half equations, half reactions, remember, you don't have to balance an entire thing like we did. You don't have to worry about if it's in acidic or basic solution. You need to take two half reactions and add them together. Make sure your electrons equal so that you can cancel them out. And then the last thing with redox. We did not get to redox titrations this year. So this kind of ties into 4.6 and 4.9. We did titrations with acids and bases. You can also do titrations with redox. Titrations are nothing more stoichiometry. If you have a redox titration, the purpose of the titration is the same thing. You're determining the concentration of something. You have, in this case, if we have potassium permanganate, we know the concentration of that. We have a substance down in the flask. This we don't know the concentration of. And so we can add known concentration to this solution in order to figure out the concentration. Remember, at the equivalence point, we use the mole ratio. At the equivalence point, we just do stoichiometry. And then molarity is moles per liter. So if we know the volume of the substance that we had, and we stoich to moles, we can find the molarity. So titrations are nothing more than stoichiometry. And what this last slide shows is the difference between an acid-base titration and a redox titration. They both are stoichiometry. They both are used to determine concentration. The only difference is one of them is neutralization, one of them is redox. They're still used to determine the concentration of an unknown. And this shows some different examples, but both of them are used stoichiometry to figure out an unknown.